Good afternoon, dear students. We are in discussion with the nuclear physics, 10th standard. Already you had 2 sessions where you had discussions with radioactivity and types of radioactivity, natural and artificial radioactivity, and then their units. Also you had a discussion related to the decay processes, alpha, beta and gamma decay processes. Also you had discussion with the nuclear fission and the fissile materials. Now we are going to start with the chain reaction, which clearly explains about the fission process which is carried out in nuclear reactors as well as in atom bomb. And then we shall discuss about atom bomb, and then we shall speak about nuclear fusion reaction, which is otherwise called as thermonuclear reaction in this session. We shall start from nuclear fission. The phenomenon of splitting up of heavier nucleus into 2 or more lighter nuclei of comparable masses with release of large amount of energy along with the 3 neutrons is called nuclear fission. So what will happen if a neutron bombards a uranium-235 nucleus? It gets split up into 2 fission fragments. One is barium, another one is krypton, along with the release of 3 neutrons. This is what we called as nuclear fission reaction. A fission produced with a single uranium-235 nucleus has no use at all. If this process continues, if this process goes on continuously, then that will be much helpful in the construction of nuclear reactor, also in atom bombs as well. We are going to speak about the chain reaction process which is taking place in both nuclear reactor as well as in atom bombs. First one, chain reaction. What is a chain reaction? As we saw in nuclear fission, a neutron, when bombards the uranium-235 nucleus, which is the fissionable nucleus, gets split up into barium and krypton, 2 fission fragments. Along with the 2 fission fragments, we have 3 neutrons. What these 3 neutrons will do if there is an existence of further uranium nucleus? These 3 neutrons in turn collide with the other 3 uranium-235 nucleus. Other uranium-235 nucleus producing 3 neutrons each. 3 neutrons each. So in each fission we have 3 neutrons. 3 fissions have taken place. So a total of 9 neutrons will be obtained in the second step, along with the 2 fission fragments in each fission, but I am not mentioning that. Along with the 2 fission fragments will be there, but apart from fission fragments, I am focusing about the number of neutrons produced. So what happened? There are 3 neutrons in first fission. These 3 neutrons in turn undergo 3 fission reactions with the 3 uranium-235 nucleus, so that 3 neutrons are produced in each fission process, so that a total of 9 neutrons are produced in the fission reaction in the second step. And then this 9 neutrons in turn produces 21 neutrons. This 21 neutrons in turn produces 81 neutrons, and so on. This is called a chain reaction. And a chain reaction is a self-propagating process in which the number of neutrons goes on multiplying rapidly, almost in a geometric progression. So I would like to define once again what is a chain reaction. A chain reaction is a self-propagating process in which the number of neutrons goes on multiplying rapidly, almost in a geometric progression. What is the geometric progression for a 3 neutron fission here? I can write it as 3 power n. 3 power n. If n equals 1 in the first step, in the first fission, number of neutrons produced is 3. If n equals 2, the number of neutrons produced is 3 power 2, 3 square, which is 9. If n equals 3, then 3 power 3, 27. In this way, you can write the number of neutrons produced in each and every successive step. So the geometric progression for a 3 neutron fission is 3 power n. If 2 neutrons are produced in each fission, then the geometric progression we used to call GP is 2 power n. Is 2 power n. If there are 5 neutrons produced in each fission, then the geometric progression is 5 power n and so on. So the number of neutrons produced at the second step or fifth step or at the eighth step can be easily calculated or easily found using the geometric progression. There are two kinds of chain reaction. A chain reaction are of two types. One is controlled chain reaction, another one is uncontrolled chain reaction. One is controlled chain reaction and another one is uncontrolled chain reaction. What is a controlled chain reaction? In a controlled chain reaction, if 2 or 3 neutrons are produced in a nuclear fission reaction, the number of neutrons which are allowed to carry out the further fission reaction is maintained a constant and is almost equal to 1. So the number of neutrons is maintained to be equal to 1. So what about the other neutrons which are produced during the fission reaction? Those neutrons are absorbed by the suitable absorbers of neutrons so that they will not be allowed to proceed further with further fission reactions. Only one neutron is left which is allowed to carry out further fission chain reaction. In this kind of fission chain reaction is called controlled fission chain reaction. In a controlled fission chain reaction, the energy obtained can be used for constructive purposes, and a controlled chain reaction is used in the base of construction of nuclear reactors where the energy is produced in a sustained and controlled manner. What is meant by sustained? What is meant by sustained? Sustained here refers to continued, to be continued or proceeded further and further, is carried out further and further. So you can go on with a simple example here. You just imagine a snow bowling ground here, a snow bowling arena, where the bowler used to bowl different sizes of balls, and the bowling pins will be arranged in an order like this. I can show you like this. There will be a bowling pin like this, and then it is followed by 2 bowling pins. So when one hits the other, then the 2 will fall down. This 2 will hit 4 and the 4 will hit 8 and so on. So when the bowling ball hits 1, then it will be continued further and further so that all the balls will, or all the pins will fall down. That's a very simple example to explain chain reaction. So in a controlled chain reaction process, the number of neutrons which are used to carry out further fission is maintained to be equal to a constant and is equal to 1. The number of neutrons producing fission is equal to 1. Second thing, the neutrons which are available in the fission reactions are absorbed by suitable absorbance of neutrons, so that 2 neutrons will be absorbed. Only 1 neutron, the excess neutron, is absorbed. Only 1 neutron is allowed to carry out further fission chain reaction. As we are controlling the number of neutrons carrying out further fission, we used to call them as controlled fission chain reaction. It's called controlled fission chain reaction. The energy produced in a controlled fission chain reaction is used for constructive purposes. Example, the controlled fission chain reaction is used in the construction of nuclear reactors, in the construction of nuclear reactors, where the energy produced is sustained and in a controlled manner. So that is about controlled fission chain reaction. What about uncontrolled fission chain reaction? What about uncontrolled fission chain reaction? In an uncontrolled fission chain reaction, all the neutrons produced will carry out further fission reactions. So the number of neutrons will be produced rapidly, and the fission reactions are also carried out very rapidly, and enormous amount of energy will be released within a very fraction of a second. Fraction of a second. So just imagine, enormous amount of energy will be produced. You might have learnt in the previous session that in each fission reaction 200 million electron volt energy is produced. If multiple number of fission reactions are carried out in a fraction of a second, then you just imagine the amount of energy that is released during the uncontrolled fission chain reaction. So in an uncontrolled fission chain reaction, all the neutrons which are available are allowed to carry out further fission chain reaction. So the reaction will be continued further and further. So the number of neutrons produced and the number of fission processes taking place is taking place rapidly. It's taking place rapidly. Rapid production of neutrons will take place. Rapid, nuclear fission reactions are also taking place, so that the energy produced will be more in number. Energy produced will be enormous, and that will be released within a fraction of a second. Where this uncontrolled fission chain reaction is used? This uncontrolled fission chain reaction is used in the construction of atom bomb. The uncontrolled fission chain reaction is used in the construction of atom bomb. So we can say in a controlled fission chain reaction, number of neutrons producing fission reaction is 1. Here the number of neutrons undergoing fission reaction is all the 3, if it is a 3 neutron fission. If it is 2 neutron fission, then we can say it is 2. Where do you use this controlled fission chain reaction? In a nuclear reactor. In a nuclear reactor. In this case, in an uncontrolled fission chain reaction, it is the base for the construction of an atom bomb. So you can just list out, we can distinguish this controlled and uncontrolled chain reaction like this. Even this controlled chain using a controlled chain reaction, we can use the energy obtained for constructive purposes. Here, if you are using an atom bomb, obviously it is very clear that the energy produced is for destructive purposes. Right. This is all about a chain reaction and its types. So what is a chain reaction? A chain reaction is a self-propagating process in which the number of neutrons goes on multiplying rapidly, almost in a geometric progression, and the types are controlled and uncontrolled fission chain reactions. Fine. We shall now speak about critical mass. The mass corresponding to a critical size is called critical mass. What is meant by critical size or critical mass? We shall speak out here. Simple. As we saw, in a nuclear fission reaction, either a 2 neutron or 3 neutron fission will take place. On an average, you will get 2.5 neutrons. That doesn't mean that 2.5 neutrons will be released. No, which means either you will get a 2 neutron fission or a 3 neutron fission. All these available neutrons may not undergo further fission reactions. They may escape out of the system. If they escape out of the system, chain reaction will not be possible. If the neutrons may escape or undergo escape, we used to call them as leakage of neutrons. We used to call it as leakage of neutrons. Not only the escape of neutrons will not result in a further chain reaction, also these neutrons which are available may be absorbed by non-fissionable materials. Non-fissionable materials. A non-fissionable material, when absorbs a neutron, it will undergo a transition to other nuclei. For example, if a neutron is absorbed by uranium-238, then it will get transformed to neptunium-239 and then to plutonium-239, like this. A transformation of element or transformation of nucleus will take place by the absorption of neutrons. Finally, you will be getting a fertile material which is used to carry out further fission reactions. That is different. But what happens here is that in the availability of neutrons, we may not expect all the neutrons to carry out further fission reactions. It may not be possible. They are not continuously producing further fission reactions. Reason is, either they may undergo a leakage. Leakage in the sense they may not undergo, or they may not produce further fission reaction, and they may escape out of the system. Because of the escapism of neutrons, there will be no further fission chain reaction. Second thing is that they may be absorbed by non-fissionable materials available in the fuel. So because of the absorption of neutrons by non-fissionable materials, the availability of neutrons is less in number, so the fission chain reaction will not be continued further. So what happens is that the chain reaction will not be sustained. Chain reaction will not be sustained. In order to sustain a chain reaction, what should be done, or what we have to maintain? In order to sustain a chain reaction, the rate of production of neutrons, we can say here, in order to sustain a chain reaction, the rate of production of neutrons must be greater than the rate of loss of neutrons. The rate of production of neutrons must be greater than the rate of loss of neutrons. So the number of neutrons produced must be more, and the rate of loss of neutrons must be less in number. So in order to sustain a chain reaction, this condition must be maintained. Also, the mass of the material, the size of the material must be equal to some optimum value. The mass of the material, mass of the fissile material is equal to some optimum value. We used to call this as critical mass. We used to call this as critical mass. In a funny way, we can speak about this critical mass. If you are having your breakfast, if 4 idlis are sufficient enough for your breakfast to fulfill your hunger, then the 4 idlis whose size is called the critical size, and the corresponding mass for those 4 idlis is called critical mass. It's very simple. So if 4 idlis are sufficient enough to fulfill your hunger, then we can say their size is called critical size, because it is enough to fulfill your hunger. And the corresponding mass, if you weigh that 4 idlis, then they will be giving you some mass, right? And that mass is called critical mass. In the same way, if you are taking some quantity of fissile material, then you used to call it as critical size, and the corresponding mass is called critical mass. So the mass of the fissionable material must be equal to some optimum value, some required value. Then you can carry out the fission chain reaction further and further. You can sustain the chain reaction. So the optimum value of the nuclear fissile material is called critical mass. So we can have a look here. What is critical mass or critical size? As you know, in a nuclear fission reaction, either a 2 or 3 neutron release will take place. All the neutrons may not be available to carry out further fission chain reactions. Some of the neutrons may escape out of the system. We used to call it leakage of neutrons. And some other neutrons will be absorbed by the non-fissionable materials. This too leads to the loss of neutrons. Since the neutrons are lost, the fission chain reaction cannot be carried out further. So in order to sustain a chain reaction, very first thing what is required is the rate of production of neutrons must be greater than or must be more than the rate of loss of neutrons. And second thing, the mass of the fissionable material taken must be equal to some optimum value. See, this one must be equal to some optimum value. We call this optimum value of fissile material as critical mass. So now we shall define what is critical mass. We shall now define critical mass. The minimum mass of the fissile material necessary to sustain the chain reaction, is called critical mass, which is denoted by M suffix C. So the minimum mass of the fissile material necessary to sustain the chain reaction is called critical mass. See this one, the minimum mass of the fissile material necessary to sustain the chain reaction is called the critical mass MC. What are the factors to which the critical mass of the fissile material depends upon? First one, it depends upon the nature of the material, depends upon the density of the material, also it depends upon the size of the material. Depends upon the size of the material. So the critical mass depends upon the nature of the fissile material, density of the fissile material, and size of the fissile material. So how will you define the minimum mass of define critical mass? The minimum mass of the fissile material necessary to sustain the fission chain reaction is called the critical mass, and it depends upon the nature of the fissile material, density of the fissile material, and size of the material. So this is the definition. So the minimum mass of the fissile material. Then if the size of the fissile material, or in other words the mass of the fissile material, is less than the critical mass MC, then we used to call this fissile material as subcritical. If the size of the fissile material or mass of the fissile material is less than the critical mass, then it is called subcritical mass. If the size or mass is greater than the critical mass, then we used to call this mass as supercritical mass. So if a fission chain reaction must be carried out, the basic requirement is the mass must be equal to the optimum value. We used to call it critical mass. If the mass of the fissionable material is less than the critical mass, then it is called subcritical. If the mass of the fissionable material is greater than the critical mass, then it is called supercritical, right? So you have to define what is the critical mass, and then what are the factors to which the critical mass depends upon, and then what is subcritical fissionable material and supercritical fissionable material. When do we say a fissionable material is subcritical? When the size of the fissionable material is less than the critical mass. If the size of the fissionable material is greater than the critical mass, then we call it supercritical. Now we shall speak about the atom bomb and its working. What is an atom bomb? Generally speaking, what are the fundamentals which with an atom bomb is working? An atom bomb is working on the basis of uncontrolled fission chain reaction, as we mentioned earlier. We shall speak about the atom bomb now. As I mentioned, in an atom bomb, the basic principle involved is uncontrolled fission chain reaction. Is uncontrolled fission chain reaction. Atom bomb works on the principle of uncontrolled fission chain reaction. The number of neutrons which are produced will go on multiplying indefinitely, as well as the fission process will also be carried out indefinitely, almost in a geometric progression. So the number of neutrons and the nuclear fission reaction goes as a geometric progression. So the energy released will be in the form of explosion. So we shall say atom bomb is an explosive device. Atom bomb is an explosive device. It works on the principle of uncontrolled fission chain reaction. The number of neutrons produced and number of fission reactions carried out at the time of bombardment of atom bomb goes as a geometric progression. It goes on multiplying indefinitely. So the energy released will be in the form of explosive. So it is an explosion type. Atom bomb is an explosive type. We shall speak about the construction and working. Construction of an atom bomb. Construction of an atom bomb. It consists of a fissionable material or fissile material, which is a subcritical mass. Subcritical mass, this is fissile, and it has a void. Void here refers to a small opening. A void refers to a small opening. And we can say here this is placed in such a way that the void can be filled by another cylinder. Another cylinder of a subcritical mass, we can say here. This is a fissionable material. This is made of uranium, or this is uranium-235 material, or otherwise you can have plutonium-239 here. So this is also uranium-235 or plutonium-239, but this is also subcritical mass, and there is some kind of explosion. Conventional explosive is there. So we can say here there is a cylindrical or there is a fissile material which is a subcritical mass, which is taken in the form of subcritical mass. This material has a void which is in the form of a cylinder. Actually, this is in the form of a cylinder. This cylindrical void can be filled by another cylindrical mass here, which is kept at a far off distance, means at some distance. And if the bomb has to be exploded, first thing, a conventional explosive must be exploded. A conventional explosive here can be taken as TNT, trinitrotoluene explosive. If a TNT explosive is exploded, then it produces it provides a pressure over this subcritical mass, so that this subcritical mass will be propelled. It will be propelled so that it will move, and then it will go and fuse into the void of this mass, which is subcritical. This is also subcritical. So it gets propelled and then comes and fuse over here. So what will happen? This subcritical mass and this subcritical mass, when fused, will become supercritical mass. If the mass becomes supercritical, then explosion will take place. So if an atom bomb is to be exploded, simple thing is that a conventional explosive must be exploded first, and then that will propel the subcritical cylindrical mass so that it will be propelled and it will fuse into the void of this subcritical masses, so that the total mass now becomes supercritical. So with the availability of neutrons, the fission chain reaction will be carried out almost rapidly. An uncontrolled fission chain reaction will take place so that it will explode. So an explosion takes place. If the bomb is exploded, what are the changes that you observe at the surroundings? If the bomb explodes, what will happen? Enormous amount of heat, light and radiation will be given out, which we cannot withstand. Then second thing, temperature will be raised to millions of degrees. And then pressure will be raised to millions of atmospheres. Millions of atmospheric pressure. And then we can say hazardous radiations will be given out. Along with emission of gamma rays, which has a very high penetrating power. Even it will disrupt the entire normal functioning of the biological system. It will be disturbing the entire functioning of the living beings. So hazardous radiations will be given out along with gamma radiations. So what will be the effect? It will be destroying the tissues in the human body. It causes mutation which pass on from generations to generations. So dangerous radiations will be given out. So what are the changes that will that will be observed in the surroundings at the site of explosion of atom bomb? Large amount of heat, light and radiation will be given out. The temperature will be raised to millions of degrees. Pressure will be raised to millions of atmospheres. Hazardous radiations will be given out along with the gamma radiations, which will affect the entire normal functioning of the biological system. Total biological system will be disrupted. And you might have heard about the explosion of this kind of atom bomb in 1945 at Hiroshima and Nagasaki in Japan, which is considered as a revenge taken by USA for the Pearl Harbor attack made by Japan in Second World War.
The gun method. The gun is considered the simplest way to build a nuclear weapon. The weapons consist of a tube in which one half of the nuclear charge is fixed at one end and the other half is at the opposite end. An explosive is placed behind the other half of the nuclear material. When the explosion is detonated, the nuclear charge races down to the other end. Once these two halves meet, the chain reaction starts and the explosion takes place. The second approach is the implosion method. In this approach, the nuclear fuel is shaped into a sphere called the pit, and the explosives are placed around it. When these explosives are detonated, the force squeezes the pit and the explosion takes place. The explosion should be placed in such a manner that the shock waves generated should be precisely spherical in shape and detonate at the same time.
So far we have discussed about the fission of heavier nuclei into lighter ones. There is a reverse idea where the lighter nuclei can be combined together to form heavier ones. If heavier nuclei split up into lighter nuclei, then we used to call it nuclear fission. Fission in the sense splitting up. And if lighter nuclei are combined together to form a heavier nucleus, we used to call fusion, nuclear fusion. Fuse, it means combined together. So if heavier nucleus split into lighter ones, we call it fission, nuclear fission. If lighter nuclei combine together to form heavier ones, we used to call nuclear fusion. You just look at this term, lighter nuclei, a plural form of nucleus. So if lighter nuclei combine together to form heavier nucleus, then it is called nuclear fusion. What is nuclear fusion? I can define nuclear fusion here. Definition of nuclear fusion. If two or more lighter nuclei combine together to form heavier nucleus. If two or more lighter nuclei combine together to form heavier nucleus, then this phenomenon is called nuclear fusion. Example, a deuterium fuses with another deuterium, forms an alpha particle, He2 nucleus, along with the release of energy Q. Energy. So H12. What is this? Deuterium. This is another one, deuterium. These two fuse together. These two are lighter nuclei. These two fuse together to form a heavier nucleus. I can say alpha particle or helium nucleus, which is a heavier nucleus. And Q is the energy released. So two or more lighter nuclei. Two lighter nuclei combine together to form a heavier nucleus along with the release of energy is called nuclear fusion reaction. A nuclear fusion reaction. A typical example for a nuclear fusion reaction can be discussed here. What is deuterium actually? Deuterium is isotope of hydrogen, which is a lighter nuclei, which has one proton and one neutron. Here also one proton and one neutron. So this lighter nuclei fuse together to form a heavier nucleus. As here I have mentioned He24. In nuclear fusion reactions which are carried out in sun and stars, the fusion reaction goes like this. We can say here H12 plus H12 gives He23, an isotope of a helium, plus a neutron, plus energy. This can be shown like this: a proton and a neutron plus a proton and a neutron together. See, there are two protons and two neutrons. They combine together to form, as you know very well, this is the atomic number, this one is mass number, or otherwise you can say nucleon number. One thing you must remember, whenever a nuclear reaction is taking place, the conservative laws must be satisfied. Conservation of atomic number must be satisfied. Conservation of nucleon number must be satisfied. If this atomic number is added up 1 and 1 gives 2, then nucleon number 2 plus 2 is 4, and the product side 3 plus 1 is 4, so the reaction is satisfied. This is not a balancing reaction. This is a reaction which goes on with the conservative laws. So here a proton and a neutron, another proton and neutron combine together to form, see this one. We can show here 2 proton and 3 neutron, 2 proton and 1 neutron. We can show like this: 2 protons and 1 neutron. So atomic number refers to number of protons, mass number refers to number of nucleons. 2 proton plus 1 neutron. Actually this process will be carried out in a different way, but I am just representing here a proton neutron and a proton neutron assembly together gives 2 proton and 1 neutron combination of nucleus, which is He23 nucleus, an isotope of helium. Along with that, there is a release of a neutron, So I just split out He24 nucleus into He23 plus the neutron with the release of energy. This is how the fusion reaction takes place. Why fusion reaction takes place? How energy is released in a fusion reaction? Whether it is a fission reaction or fusion reaction, there is always a mass difference. The mass of the product nucleus is always less than the sum of the mass of the 2 lighter nuclei in a fusion reaction. You just look at the case here. If you calculate the mass of He23, I can write the condition like this: mass of He23, which is a daughter nucleus. A product nucleus is called daughter nucleus. The mass of He23 nucleus is always less than the sum of the mass of H12 nuclei, I can say. This is the parent nucleus. So the mass of the daughter nucleus is always less than the sum of the mass of the parent nuclei. There is a difference in mass. We used to call this difference in mass as mass defect. Difference in mass is called mass defect. Suppose if you are breaking a biscuit and you just want to join the biscuit once again, will the mass be the same? Definitely no. There will be some amount of crumbles which would have spilled over. The remaining biscuits alone will be combined so that their masses will not be exactly equal to the original mass of the biscuit. So the loss in mass of the crumbles will be given in some other form. You just compare that with the nuclear fusion reaction here. Actually, 2 broken parts of the biscuits are combined together to form a single biscuit. Some amount of mass is lost, and that is given out in the form of energy. How come this is possible? This is in accordance with the mass energy relation. mass energy relation. The mass that is lost is called mass defect, and that lost mass is obtained in the form of energy according to mass energy relation. What is this mass energy relation? This was first proposed by Albert Einstein in 1905. In 1905, Albert Einstein proposed this mass energy relation. He gave out an equation which goes like this: E equals mc square, which connects energy and mass. Energy and mass. And we can say here, mass can be converted into energy and vice versa. Means energy can be converted into mass. In other words, I can say mass is congealed energy. Can say mass is congealed energy.
Energy equals mass times speed of light squared. What Einstein really meant was everything around us is nothing but energy in different forms. So it is possible to convert this matter to energy and vice versa. Matter is just a condensed version of energy. We can picture this by thinking about water and steam. You heat up water and it becomes steam. You cool it down and it becomes water again. It takes a lot of steam to just get a few drops of water, but only a few liters of water to get a room full of steam.
If you want to get the energy in the form of a solid, then it is mass. Energy which you cannot see, if that must be brought into a reality, that must be brought into some existing thing, then that is nothing but the mass. So how it happens? Lighter nuclei combine together to form heavier nucleus. There is always some difference in mass. We used to call it mass defect. So the mass of the daughter nucleus is always less than the mass of the parent nuclei, sum of the mass of the parent nuclei, and the difference in mass is called mass defect. And this difference in mass, this mass defect, is converted into equivalent amount of energy according to mass energy relation. What is mass energy relation? Any amount of mass can be obtained in the form of energy, or energy can be obtained in the form of mass. This was first proposed by Albert Einstein in 1905 with his famous equation E equals mc square, which we can say mass is congealed energy. Mass is congealed energy. So energy, when taken as a solid, will be obtained as a mass. So mass is congealed energy. This is a very famous equation. If a very little amount of mass is lost, how come we get this much amount of energy, enormous amount of energy? That is very simple. This mass is coming as a product with the velocity of light square. Velocity of light square. What is velocity of light here? I can write it here. The velocity of light in vacuum, C equals 3 into 10 power 8 meter per second. Just imagine this magnitude. C equals 3 into 10 power 8 meter per second. Though the mass which is coming as a difference, mass defect, is very, very, very low in the order of atomic mass units. In the order of atomic mass units. When it is taken as a product with this 3 into 10 power 8 meter per second, that will be giving you a greater magnitude of energy. So a little amount of mass that is lost will be obtained as a greater magnitude of energy in nuclear fusion reaction as well as in nuclear fission reaction. So mass is congealed energy. This is about a nuclear fusion reaction. If this happens, or if nuclear fusion reaction is discussed, our atmosphere consists of a lot of hydrogen atoms. Why can't we expect these hydrogen atoms to get combined together and to form a heavier nucleus, and spontaneously with the normal temperature and pressures, why can't we expect a fusion of lighter nuclei to form a heavier nucleus, and an explosion sort of thing must or can take place in the space, in the atmosphere? Obviously that should happen, but we cannot able to observe such kind of spontaneous happenings in atmosphere. There is plenty of hydrogen existing. If all these hydrogen atoms fuse together, you just imagine how come the effects will be if that happens at normal temperatures and pressures. If it happens so, then we'll be getting lot many amount of explosions in our atmosphere, but that is not happening. Why? In order to explain this, idea is very simple. We are speaking about nucleus. The charge of a nucleus is positive. The charge of the nucleus is positive. A positively charged nucleus fuses with another positively charged nucleus. According to the electrostatic theory, two positively charged particles, when brought close to each other, they cannot combine together simply, just like that. They will be experiencing a greater magnitude of repulsive force. I can just show it with a simple diagram. I would like to show you with a simple diagram here. This is a positively charged nucleus, and this is another positively charged nucleus. These together to form a heavier nucleus, a positively charged nucleus. Let us say like this. Combination of these two positively charged nucleus or fusion of two positively charged nucleus at low temperatures and pressures is not possible. At pressure is not possible because there is a mutual force of repulsion between the two nucleus. There is a mutual force of repulsion that will take place between two nucleus. So they cannot combine together to form a heavier nucleus. So at normal temperatures and pressures, though there is availability of more number of hydrogen or deuterium or whatever in the atmosphere, we cannot observe such kind of explosions. Then, when it is possible, when do we expect a nuclear fusion reaction to carry out or to take place? The nuclear fusion reactions will be carried out only when the temperature is of the order of 10 power 7 to 10 power 9 Kelvin. 10 power 7 to 10 power 9 Kelvin. So, a nuclear fusion reaction will be carried out at this temperature. And the temperature is of the order of 10 power 7 to 10 power 9 Kelvin. With this high temperature, with the high pressure, we can say the positively charged nuclei are obtaining enormous amount of or sufficient amount of kinetic energy so that they can move towards each other and they can fuse together and they can form a heavier nucleus. So we can say the nuclear fusion reaction will be carried out only at very high temperatures. So we used to call nuclear fusion reaction as thermonuclear reactions. Nuclear fusion reaction as thermonuclear reactions. Nuclear fusion reaction is always called thermonuclear reaction because it is carried out only at a very high temperature of the order of 10 power 7 to 10 power 9 Kelvin. But nuclear fission reactions will be carried out at room temperatures themselves. Room temperature. In the room temperature itself, nuclear fission reaction will be carried out. But in fusion reaction, the nuclear fusion reactions will be carried out only when the temperature is of the order of 10 power 7 to 10 power 9 Kelvin and the pressure is maintained at millions of atmospheres. And what is the amount of energy released during each fusion reaction? Energy per fusion. The energy released per fusion in each fusion. Energy released in each fusion is 3.84 into 10 power minus 12 joule. 3.84 into 10 power minus 12 joule. So energy released per fusion is of the order of 3.84 in 10 power minus 12 joule. This is a important one mark question which you can answer. Energy released per fusion is 3.84 in 10 power minus 12 joule. We are expressing the amount of energy released in terms of joules. Energy in terms of joules. We can convert this into electron volts also. What is that electron volt called? We shall speak about that. So, why nuclear fusion reactions are called thermonuclear reactions? Idea is very simple. At low temperatures or ordinary room temperatures, fusion of lighter nuclei is not possible because of their mutual electrostatic repulsion as per Coulomb's law. So, if these two positive charges have to be combined, then the external temperature must be more. And these temperatures are available in two places. This amount of temperature, 10 power 7 Kelvin to 10 power 9 Kelvin. This much amount of high temperature is available at two places. One at the site of explosion of the atom bomb. So in order to fuse two nucleus, you must explode an atom bomb, or otherwise you have to go to sun where this much amount of temperature is available. So there are two places, one at the site of explosion of the atom bomb, and second thing, in sun. This much amount of high temperature is available, this much amount of pressure is also available. So since this fusion reaction is carried out at very high temperatures, we used to call these nuclear fusion reactions as thermonuclear reactions. The energy released per fusion is 3.84 in 10 power minus 12 joule. As I have mentioned, the energy released per fusion is in terms of joules, 3.84 in 10 power minus 12 joule. That is a general way of expressing the energy, but for our convenience we have to go for a microscopic scale, which is of the order of electron volts. What is electron volt? It is the energy possessed or obtained by the electron when it is accelerated by a potential difference of 1 volt. If I accelerate an electron with a potential difference of 1 volt, the energy gained by the electron is said to be 1 electron volt. The energy gained by the electron is said to be 1 electron volt. What is the equivalence between 1 electron volt and 1 joule? 1 electron volt is equal to E, refers to electronic charge, which is 1.602 into 10 power minus 19 joule. Sorry, 10 power minus 19 coulomb. And what is the potential with which this electron is accelerated? 1 volt. So this is 1.602 into 10 power minus 19 joule. 1 coulomb and 1 volt is equivalent to 1 joule. So 1 electron volt is equal to 1.602 into 10 power minus 19 joule. Which one is greater, joule or electron volt? Obviously joule is greater. Electron volt is a lesser magnitude. We cannot wear the dresses what we used in our kids level. If you are at the LKG level, you might have wore the dresses, right? That cannot be used at this level, and you cannot use your father's dress also. So it all depends upon the convenience. So if you go for microscopic scale of energy, that must be represented in terms of electron volt. Normal energy scale, joule. Higher order energy scale, kilowatt hour. It is in the order of kilowatt hour. The energy what we are getting to our household, the electricity, electrical energy what we are getting as an household is of the order of kilowatt hour. 1 kilowatt hour is equal to 1 unit, which is 3.6 in 10 power 6 joule. 1 kilowatt hour is equal to 3.6 into 10 power 6 joule, which is 1 unit. So this is a greater magnitude of energy. 1 electron volt is the lesser magnitude of energy. It is always compared to a standard, which is nothing but the joule. And also we shall have another tidbit which is there in your textbook, you can go through it. As I mentioned, in the Second World War, 2 bombs have been dropped over Hiroshima and Nagasaki. The bomb that has been dropped over Hiroshima has been given the name Little Boy, and it was a gun type of atom bomb. How? We had in the discussion that the cylindrical mass is propelled, it is fired, and it gets fused into the void. So that's a gun type of atom bomb. And then in Nagasaki, the bomb dropped has been given the name Fat Man. There it is an explosion type. There it is not a gun type bomb, it is an explosion type. A visual has been given for the types of atom bombs, gun type atom bomb as well as the explosion type atom bomb related to the atom bomb section. And also chain reaction also has been given an animation. You might have seen it. You just go through it once again, have a clear picture about what is a chain reaction, what is controlled and uncontrolled chain reaction, and then what is atom bomb, how it works, how it explodes, and what are the effects of exploding an atom bomb, and then what is nuclear fusion reaction, and then what is the amount of energy released per fusion, and why nuclear fusion reactions are not observed in our day-to-day life, because at normal room temperatures and pressures nuclear fusion reactions will not take place, It will take place only at very high temperature of the order of 10 power 7 to 10 power 9 Kelvin. So we used to call nuclear fusion reactions as thermonuclear reactions. All these ideas will be very clear. You can go through it and have a clear picture about it.